Welcome to this lecture on minimum spanning trees. To discuss minimum spanning trees, let's first talk about spanning trees. A spanning tree is a tree in a graph that reaches every node in that graph. Okay, so if this is a graph, a spanning tree for that graph might look like this, or it might look like this. The point is that I'm trying to make here that it's a tree, and therefore there are no cycles. It reaches every node, and therefore if there are v nodes, then there are, by necessity, v minus 1 edges. And furthermore, they're not necessarily unique, right? These are two spanning trees, but there could be possibly many more. Now, a minimum spanning tree takes into account the weights of the edges in the graph and tries to find a spanning tree that has a minimum total weight. Okay, so if this again is our graph, which is weighted, this is a minimum spanning tree, but so is this. And the total cost of this spanning tree is 5 plus 2 plus 1 plus 5, or 13. And same here, 5 plus 2 is 7, 8 plus 5 is 13. Okay, so these are both minimum spanning trees. So that, again, minimum spanning trees are not necessarily unique. Minimum spanning trees, or MSTs, are usually for undirected graphs, and they have a lot of applications. A lot of applications in network design. So if you wanted to connect a whole bunch of computers and you had a lot of options for how you could connect them, but you want to make sure that they can all talk to each other, the least you have to do is a spanning tree, right? Because if you don't have a spanning tree, then there are going to be some pairs of computers that cannot talk to each other. So the least number of connections that you need is a spanning tree number of connections. And this minimum spanning tree says, how do we connect all these things into a spanning tree in a way that minimizes the total cost? And that cost could be, say, the length of the network cabling between pairs of computers. You can also use minimum spanning tree as an approximation algorithm for classical graph problems like the minimum weight graph tours, like the traveling salesperson problem. Also, you can use minimum spanning trees when you're doing data cluster analysis. If you had a bunch of data points like this is up my alley because this is research that I do work in. You could have a minimum spanning tree and say these things are connected because they're close together, these things are connected because they're close together, and then maybe this is a connection. And that might be a minimum spanning tree that sort of clusters these points into different subparts of the tree or subgraphs. Okay. Now, there are two classic algorithms for finding minimum spanning trees. They are called Prim's algorithm and Kruskal's algorithm. And Prim's algorithm, which is where we'll start, is very similar to Dijkstra's algorithm, which we already know. And there are a few key differences, but if you understand Dijkstra's algorithm, you can easily implement Prim's algorithm. It starts with one vertex and it builds one tree. Okay? This is as opposed to Kruskal's algorithm, which we'll see in a minute. And then the choice that it makes is it repeatedly, until we've built a tree that spans the whole graph, we repeatedly add the vertex that hasn't been added to the tree yet, that has the lowest weight edge connecting it to the tree. And we'll see an example of this. So again, you're building a tree vertex by vertex, and at each stage you find what's the vertex that I haven't added yet that I could most cheaply add to this tree through connections to vertices in this tree. Now, Kruskal's algorithm is quite different. You start with many trees. We might call this a forest. And you think of each vertex as being a tree unto itself, being connected to nothing else. And then what we do is we repeatedly join two trees using the least weight edge among all edges. And we add that edge only if we can avoid a cycle, because we know that a tree doesn't allow cycles. And in order to do this efficiently, we have to use something called the disjoint set data structure. And we'll talk about the disjoint set in a future lecture, in the next lecture. So here's Prim's algorithm. Prim's algorithm says, and again, keep in mind, this is very similar to Dijkstra's algorithm, even though the code here looks very different. You're given a graph G, you're not given a source vertex S because you can start anywhere. So you pick any vertex R as the root of our tree, or the starting vertex of our tree. It doesn't matter where you start because you're going to have to get to every vertex anyway. So our tree right now contains only one vertex R, and it could be any vertex, and all the remaining vertices, I say except V, I should say except R here. U is the set of all vertices that remain except for that root R, okay? So U are the vertices that haven't been connected to the tree yet, okay? And then we're going to add V minus 1 edges, so we're going to do this V minus 1 times. We're going to iterate around and say, find the least weight edge from any vertex in T to any vertex in U, and then add that edge and the vertex U to the tree T, and then remove U from the set capital U. Okay, so we just do this so many times and we're left with a tree that touches everything, okay, that connects everything. And it looks different than Dijkstra's, but again, if you have Dijkstra's algorithm, you could retool it using very minimal changes. It's nearly identical code. Here are the key differences between Dijkstra's algorithm and Prim's algorithm. Dijkstra's algorithm has a specified source vertex S, and as we see with Prim's algorithm, there is no specified source. We just chose a vertex R as our root, our starting point. And then the real difference is this. In Dijkstra's algorithm, we always choose as the next vertex to explore the one with the least path cost from the source, and the source was specified as input. In Prim's algorithm, we choose the vertex with the least edge weight from any node in T to some vertex that hasn't been connected yet. Okay, so again, in Dijkstra's algorithm, the vertex with the least path cost from S to that vertex. In Prim's algorithm, the least edge weight from that vertex to a vertex in T. So in Dijkstra's algorithm, we're counting path costs. That means multiple edges from S to that vertex. In Prim's algorithm, we're thinking from a vertex in U to a vertex in T, what's that one edge cost? And let's order by that, right? So Dijkstra's algorithm, order by path cost, multiple edges. Prim's algorithm, order by edge cost, one edge. Okay, that's the key difference. So let's try an example here. Prim's algorithm on this weighted graph. Suppose that we started our Prim's algorithm with the root, I don't know, at B. It really doesn't matter where we begin here. So suppose we start with B. So we're going to put B as the root. Everything else has not been visited yet. Now, what we have now is we have B is in the tree T, and we have sort of on the frontier, we have C with a cost of 8 and A with a cost of 5. Now, why did I say 8 and 5? Because those are the cheapest ways I know to connect them to the tree T. Now, I'm going to actually remove, just to avoid confusion, I'll draw those vertices that have been added to the graph, to the tree rather, by circling them. D and E cannot be added to the tree yet because I don't know a way of connecting them yet. Now, between C and A, clearly A has the lower cost, so that's what Prims would choose first because of this edge connecting this vertex to the tree. So we'll add that vertex, we add that edge, so now our tree has cost 5, and when we do that, look what happens. We have discovered now ways to get to E, which was formerly having an infinite cost, now has cost 1 using this edge. And we can reduce the cost of C from 8 down to 2, because now we have a way of connecting C directly to A and for a cheaper cost. So again, C is still in our frontier of vertices that we might consider, but its cost of attachment has gone down from 8 down to 2, okay? The next vertex we would add is E because it has the lowest cost. And again, that's the edge cost here. There's no path cost. It's not like we're considering 5 plus 1. It's just the cost of adding E by that edge 1 with cost 1. So we'll add E, add that edge, and that leads us to be able to discover D with a cost of 5. And why 5? Well, because of this edge right here. Okay. Even though there is a 5 here, but we haven't added C to the tree yet, so the tree doesn't know how to get to use this edge yet. Okay. So now we have two vertices. We have C and we have D. C has the lowest cost using this edge. And so we'll add it to the tree using this edge. And from here, we say, well, once we add C to the tree, we could get to D in a cost of 5. Well, that doesn't lower our cost, so we wouldn't use that. And nothing else changes. So we would next add D to the tree because it's the last in our frontier. And remember, we used this edge to get there. So there's our Prim's algorithm minimum spanning tree, okay, starting at B. Now, if we had started at a different vertex, we might have gotten a different answer. Okay. Now, so let's talk about correctness. Why does Prim's algorithm find the minimum spanning tree? Well, suppose we have a partially constructed minimum spanning tree like here. Okay, D and E. Suppose that those are a part of our. Suppose that that's our tree so far. All the rest of these vertices aren't in T, but they need to be added. And Prim's algorithm adds the least weight edge that connects T and U. So let's look at this. D connects to C, which is unconnected, using a cost of 5. But that's not the least cost way, right? The least cost way of connecting C is 2, right, using this edge. And the least cost way of connecting A is 1 using this edge, okay? Now, if we chose a higher weight edge, it could be replaced by a lower weight one and lower the MST cost. So in other words, if for some reason I did something stupid like connect C using this edge, so instead of taking the next least cost edge, which would be this one, instead I took some, greater cost edge like this one, and I added C with a cost of 5. Well, later I could have come in and taken that edge away and used a different edge and actually lowered the cost from 5 down to 2, okay, which is what we wanted to do anyway. Now, in practice, this is perhaps a poor ordering of the example. In practice, I would have taken this first, so let's do that. And then next, I would take, say, this edge. But if I had taken this edge instead, I could have undone that later and reduced the cost of connecting C by using that lower cost edge, okay? So always choosing the lowest cost edge to connect to the unconnected vertices from the tree is going to give us the least cost because it improves our cost. Now, the analysis of Prim's algorithm is exactly the same as Dijkstra's algorithm, and it depends on our representation and, in addition, whether or not we use a priority queue. So it's the same E log V or V squared if we're using a list with a priority queue or a matrix without a priority queue. Okay. Now let's move to Kruskal's algorithm. Here's the recap of what we said before. Start with many trees. In other words, every vertex is a tree. And then we repeatedly join two trees with the least weight edge and avoiding cycles if they could occur. And in order to make this efficient, we'll have to use a disjoint set. Okay, so here's Kruskal's algorithm. Kruskal's algorithm starts by sorting all the edges by increasing weight, all of them in the entire graph. And then we're going to visit all of those edges from U to V in increasing weight order. And then ask the question, are U and V already in the same tree? In other words, is there already a path between them? If there is not a path between them, if they're not already part of the same tree, because remember we're building small trees into larger trees and larger trees, and we're joining them together, If U and V are not part of the same tree, then we join their trees using the edge UV, okay? So let's look at this example again. With Kruskal's algorithm, again, we'll start with sorting all of the edges. So the least weight edge is 1, and so we would begin there. And we ask the question, are A and E part of the same tree? Well, initially, A, B, C, D, E are all separate trees, so they're not the same tree. So we would add this edge to join together A and E. Oops. Goodbye. The perils of lecturing outside. You get potato bugs on you sometimes. Okay, so now we've gone from 5 trees, a forest of 5 trees, down to 4 trees. We have the trees AE and the trees B and C and D. Now the next least weight edge is either AC or EC, and it actually does not matter which one you choose first. So, for the sake of argument, let's suppose we took EC next, okay? And I can do that, by the way, because E and C are not part of the same tree. Okay, so now we've gone from 5 to 4 to 3 trees. The 3 trees are B by itself, AC or AEC, and then D. The next least cost edge is this 2, okay? But I don't want to add that edge. And the reason I don't want to add that edge is because that would create a cycle in this tree, and trees cannot have cycles. We need to expend that edge, not to create a cycle, but to connect to further parts of this graph so we can get a spanning tree with V-1 edges. So I consider, but do not use this edge 2. So next, the next least cost edge is, let's say we've got 3 edges of cost 5. Let's suppose we take this one next. I don't know, DE. It does not matter which one we take. So we'll take DE. And D and E were part of separate trees, so we add them. Okay. And let's suppose that we consider this edge next with a cost of 5 again. Well, we wouldn't add that edge. Why? Because that would create a cycle, because C and D are already in the same tree. The next least cost edge, cost 5, is AB, and clearly B and A are not part of the same tree. So we add that edge. Now, at this point, we could stop, but just for completeness, we can stop because we've added V-1 edges. But we could, consider this edge, this last edge of 8. But you can see that obviously it would create a cycle, and we wouldn't add it. Okay, so this is the way that Kruskal's algorithm works. The correctness argument for Kruskal's algorithm is Kruskal's repeatedly adds the least weight edge that doesn't create a cycle. Okay, so this example is slightly changed here. I've changed this, what was a 5 to a 1. Okay, but the argument here is that if we had, at this stage in the algorithm, if we had created the tree CD and AE and B by itself, if we skipped an edge and added a greater weight edge, so what do we mean skip an edge? Well, suppose that, we skipped this 2 and we skipped this 2 and we added this 5 instead, okay? Well, we could always, that joins these 2 trees, but we always could have come back and done this edge instead and joined the same 2 trees for a lower cost. Okay, so it always benefits you to choose the lowest cost edge to join 2 trees that are not already joined, so long as you don't create a cycle. So that's why we order them by weight and then take them by weight. Okay. Now, the overall runtime of Kruskal's algorithm is E log V. And that E log V, surprisingly, comes from the sorting of all the edges. The sorting of all the edges. Now, how many edges are there? There are E edges. What is the running time of sorting N things? It's N log N. So we have, in essence, we have E log E, but we know that E is upper bounded by, V squared, right? So if we took this E and replaced it by V squared, that 2 can come out, and then we are left because it's a log, and we're left with E log V. Okay, so the sorting of the edges is actually the dominant thing that for the runtime of Kruskal's algorithm, which is a little surprising since the rest of the algorithm seems more complicated. We also have to visit all the edges. There are E edges. Once we've sorted them, we can do them in order. And for each edge, we have to ask this question: does adding this edge introduce a cycle? How quickly could we answer that? Don't know. It might sound simple, but it's actually a deep question. And how quickly could we add the edge to the tree? Again, don't know. It sounds simple, but if I were to take you through sort of a detailed analysis, we don't actually have the tools to do this to answer both of these questions efficiently at the same time right now. Okay. Now, in order to do both of those things that I've highlighted here with question marks efficiently, we know how. Let me put it this way. I could show you ways to do one of them efficiently or the other one efficiently, but not both at the same time. In order to do both efficiently at the same time, we need something called the disjoint set, which we'll talk about in the next lecture. And looking ahead, so that we can complete the analysis of Kruskal's algorithm right now, the disjoint set will allow us to answer this question and this question in what's known as log star of V time. That's not log of V, that's log star of V. And for all practical purposes, you will never see log star of V be any greater than a small number, a small constant. So it's in essence constant time. So when I say Kruskal's algorithm runs in E log V, that's because of this. And then we have order E times each of these being log star V. Well, that's effectively constant time. So really it's the E log V that dominates the runtime. Okay. Now, one last comment on minimum spanning trees. Turns out that they can handle negative weight edges just fine. Remember that Dijkstra's algorithm cannot handle negative weights, but Prim's algorithm, which is just like it, and Kruskal's algorithm can. Okay, and the reason is this: MST algorithms, they find a minimal sum of edges, but there's always the same number of edges in the spanning tree. There's always V minus 1 edges because we have to connect all V vertices, and we can't have a cycle. So that's what we say here. An MST always has V minus 1 edges, and when we're talking about shortest paths, the shortest path between two vertices could have, 1 edge or 10 edges or 100 edges. It has a varying number of edges. And so earlier, when we talked about Dijkstra's algorithm, we said, would it be possible to get rid of the problem of negative weight edges by adding a constant so that none of the edges are negative weight anymore? And that didn't work because for longer paths that used more edges, it impacted those path costs more because you're adding the same constant over and over on each of those edges. But with a minimum spanning tree, you always end up with V minus 1 edges, no matter what you do. So one way of thinking about this is that you could add that constant to make sure that every edge has non-negative cost or weight. I'm not actually saying you have to do that, but this is an effective way of thinking about the problem. Negative weight edges don't matter because we're not summing along some path, we're just totaling up all of the edges. And whether or not some of those edges are negative actually doesn't matter. And if you were to adjust those weights so that none of them are negative by adding a constant to all of them, you're still adding a constant to only V minus 1 exactly edges every time. And so that's it. Now, we've sort of left you hanging with the analysis of Kruskal's algorithm. So come back for the next lecture when we talk about the disjoint set, which is a really cool data structure, very simple, and allows us to implement Kruskal's algorithm efficiently.